All right, guys, so this is going to be an example of a conservation of energy problem. So it says, as a prank, the class decides to throw a large 2-kilogram water balloon off the school roof at Mr. Celona. The building is 12.0 meters tall, and Mr. Celona is 1.8 meters tall. If the water balloon is tossed at 10 meters per second, how fast will it be going when it hopefully hits him? All right, so this is a situation in which we can figure out how fast that water balloon will be going, knowing that potential energy as the balloon drops is going to turn into kinetic energy along the way. So we're going to use this same concept that we've been talking about to be able to figure this out. All right, so when we do conservation of energy problems, the first thing that we want to do is to set up our chart, and the chart is going to include several variables, okay? So what we're going to put in is we're going to put in potential energy, we're going to put in kinetic energy, we're going to put in total mechanical energy, we're going to put in the height, and we're going to put in the velocity. Okay. Now, based on how many different locations there are in the problem, that's going to determine how many columns are going to be in your chart. So in this case, there are 2 locations, all right, from the top of the school, right, and then when it hits the teacher at the bottom, okay? So I'm going to set up 2 additional columns. One of these is going to be for the top. I'm going to use a different color here. So this will be at the top of the school building. And then over here will be at the bottom where it hits him in the head. Okay. All right, now, on the side over here, I already wrote down a reminder of our equations for potential energy, kinetic energy, and total mechanical energy. Okay, so we know the mass. It's given over here as 2 kilograms. Okay. The building is 12 meters tall, so that's the height at the beginning. I'm going to record that in here for the beginning height, and then the ending height is 1.8 meters. All right, so I'm going to put that in here. Oh, this is meters. Okay. It also says the water balloon is tossed at 10 meters per second. That's off the building. So the original velocity at the top was 10.0 meters per second. So the very first thing that I want to do is take any relevant information that we know from the problem and get that into the chart where it belongs. All right, so the height at the beginning, the velocity at the beginning, and the height at the end. The ultimate question is how fast will it be going at the end? So this is what we're trying to figure out in the end. Okay? So in order to do that and get that step, we're going to have to go through these steps along the way. All right? So the first thing we'll do is we'll calculate the potential energy of the object when it's 12 meters up in the air. So we see here potential energy equals m times g times h. Okay, so I'm going to do 2 kilograms times 9.8 meters per second squared times the height, which is 12 meters. Sorry, 12 meters there. Okay, let's pull up the calculator here. So I'm going to put that here, 235.2 joules. All right, I can also calculate the potential energy at the end because I know the height at the end. So I'm going to do it again. 2 kilograms times 9.8 times 1.8 meters. All right, so if I do that, 2 times 9.8 times 1.8 is 35.3 joules. Okay, so I'll put that in for the potential energy here. Okay, also notice that I know the velocity at the beginning, and I can calculate kinetic energy based on that. All right, so I'm going to change colors here, and I'm going to do kinetic energy. 1/2 the mass times the velocity squared. Okay, so 10 squared is 100 times 1. We get 100 joules. Okay. So at this point, here's the deal. I know what the potential energy was at the beginning, and I know what the kinetic energy was at the beginning. So I can add these to get the total mechanical energy. So that gives me 335.2 joules. Okay. Now, if there's no friction, if there's no air resistance, there's no applied force once the ball leaves the person's hand, then the mechanical energy is going to be conserved. So that total mechanical energy column, guys, we can expect that column to stay the same all the time as long as there's no friction, applied force, or air resistance. Okay? So we're going to put that in here as well. Okay? Now remember something. Potential plus kinetic has to add up to the total mechanical energy. Take a look right here. The 35.3 joules of potential energy that I have at the bottom, plus however much kinetic energy, has to add up to this number. So that means 335.2 minus 35.3 has to be equal to the kinetic energy at that spot. So if we subtract these two, we can get this this kinetic energy. All right, so that's going to be 299.9 joules. Okay. So now I'm almost done. I have everything filled out except for this velocity. I can get that velocity because I know the kinetic energy is about 300 joules, just under, and I know the mass is 2. So I can solve this for V. So that's exactly what I'm going to do. What I'm going to do to set it up is I'm going to take that kinetic energy, 299.9 joules, equals 1/2 the mass, which is 2 kilograms, times the velocity squared. I don't know what the velocity is yet. Hold on. Let's get this out of the way. Okay, so let's solve this out. Half of 2 is just 1. So 299.9 joules equals 1 V squared. Divide both sides by 1. 299.9 joules equals V squared. And if we want to get rid of a squared, we have to take the square root of both sides. So we take the square root of this, take the square root of that. I take the square root of 300. Let's see. Whoops. So let's do square root 299.9. I get 17.3 meters per second. So that is the speed at which it will hit Mr. Celona. Notice it's faster than it was thrown, which makes sense. It's falling downwards. It's going to get faster as it goes because gravity is going to speed it up. Okay, so every one of these problems you're going to be working through using this potential energy based on the height, kinetic energy based on the speed, and the total mechanical energy being the sum of potential and kinetic. And you want to keep in mind that that total mechanical energy is going to be conserved. It's going to be the same amount before and after, as long as there's no friction, air resistance, or applied force. And in the examples we do in the beginning, we're not going to have any of those things. So these two numbers will be the same. Later on, if they are different, the difference is going to be in the amount of work that's done by one of those external forces, like we saw in the bar charts.